Good evening, everybody, and welcome to the Lunar and Planetary Laboratory and our evening lecture series. And we are happy to see so many of you here, so thank you all for coming. And before we get started, I have just one announcement to make. So if you are a student and you need a stamp for your homework assignment, we have people outside in the lobby to do that for you after the lecture. So now, it is my great pleasure to introduce tonight's speaker, Professor Jack Holt, who is an expert on solar system ices here on the Earth and on Mars. And he joined us earlier this year with a secondary appointment with the Department of Geosciences. And we were lucky to have him move here from University of Texas, where he was a research professor. And Jack has extensive fieldwork experience studying terrestrial glaciers, for example, in Alaska and in the Antarctica. And he is a co-investigator on the Charad radar sounder on the Mars Reconnaissance Orbiter that aims to map ice deposits on Mars. And he belongs to the Earth Dynamics Observatory, which is an interdisciplinary initiative here at the U of A that focuses on efforts in Earth and planetary sciences, and specifically remote sensing of global and planetary changes. So without further ado, I give you Jack Holt, and he's going to talk to us about probing glaciers on Earth and Mars.
Thank you, Tommy, for the nice introduction. Thank you all for coming. I appreciate you coming out in the evening, and I'm excited to tell you about what I think is some pretty cool work going on by myself and my students and others. And so on that note, I just want to point out that this wouldn't be possible without contributions from a lot of people. These are some of the key players. I've got more to thank at the end of the talk, but my students, Eric Peterson, Michael Christofferson, Stefano Nerozzi, Tyler Ming, Brandon Tober, some of whom are in the audience right now, and can probably answer questions better than I can. And some colleagues elsewhere, Chris Larson and Martin Trufer at University of Alaska Fairbanks, and Joe Levy at Colgate. So we're going to start on Earth and go to Mars and come back to Earth. So fasten your seatbelts. It won't be slow. So first off, what is a glacier? How many of you have seen a glacier? Wow, that's a lot of you. How many of you have been on a glacier? Okay, forget it. We can skip that. All right, maybe not. Basically, you need to start with a lot of snowfall, and it builds up, and then it gets denser and denser, and you form ice crystals, which then congeal, and you end up getting ice with air bubbles. That happens down around 50 to 100 meters, depending on where you are and the conditions. But basically, that's how you get glacial ice. And then you have enough glacial ice, it starts deforming under its own weight, and if there's a slope, it'll move downhill. So this really fancy diagram shows it well. You need an accumulation area where you build up the snow and turns into ice, flows downhill, and you have an ablation area where you lose ice either through melting or sublimation or calving off the end or maybe all those things. If everything's in balance, then it just kind of looks like this. It reaches a steady state and doesn't really change. If you add more accumulation, it starts advancing. If you start melting more off the ends and off the top and calving, then you're accumulating, then it starts retreating, which is pretty much what's happening worldwide right now. Here's a couple of examples. I'm going to show pictures pretty much exclusively of glaciers in Alaska because I've been working there the most recently, and that's where the new information is that I want to show you. So on the left, two examples, one looking down glacier from up in the catchment accumulation zone down to where it goes all the way out to terminate near the ocean. And then this is looking up glacier where you can see a couple of glaciers merging and then collecting rock and forming this moraine where you're shedding rock off the mountains and it collects on the edges and it merges. So those are just a couple of views of glaciers in Alaska. There's lots and lots of them there. So you start out up at the top. This is on the Bering ice field, very quiet, quiescent. The ice is flat and smooth, not a lot going on. This is actually really, really a big ice field. It's the largest non-polar ice field in the world. So after Antarctica and then Greenland, you've got Bagley. That feeds into a bunch of glaciers. So you start moving downhill, things start getting a little more interesting. Start getting crevasses here and there where the ice is shearing. And basically it's ductile flow or plastic deformation down at the bottom, but at the top it's still brittle, and so it's breaking into these crevasses. And crevasses are cool. This is a surging glacier, so it's going really fast, and it's just completely broken up. It's crazy. You can also get some really cool patterns in the crevasses where the ice is shearing and pulling apart, and people just study even just the shapes of these crevasses and learn about the ice. Show you a couple little video clips flying along. This is over Hubbard Glacier, which is a pretty active glacier in southeast Alaska. So down towards the terminus, very, very crevassed. And we're flying about a couple hundred feet over the surface. Another little clip. Not a good place to lose the engine. Just massive crevasses. And then down towards the terminus. Try to pause this one when we get off the edge. So this is where Hubbard Glacier meets the ocean. Tide's out right now. There's a lot of water, but it calves right into the bay there. And so you can see the really massive blue pure ice down here at the bottom, and it gets up, grades up into the crevasses, and then you would see snow on top if you go up higher, but this time of year there's no snow right at the surface. Okay, so why do we study glaciers? Lots of reasons. For Earth, it's, for Mars too, it's an important part of the climate system. It's part of the hydrologic cycle. The ice gets transported into the ocean through the atmosphere back to snow, and it's part of the whole cycle. They're retreating rapidly everywhere, so we're trying to understand how that's happening. And we need to understand how much they're going to contribute to global sea level rise and how fast. So we're doing a lot of measurements for those reasons. Plus, I think they're pretty cool. They change fast. They're one of the geologic processes that is very rapid. You can observe it. And glaciers are the biggest erosive agent on the planet. They basically bring down huge mountain ranges and enable landscape evolution on scales, on rates that are just unheard of otherwise. So how do we study glaciers? So lots of ways to get their velocity. It's generally done from satellites, like images, and you can repeat the images and then track features on the surface. You can use radar and do kind of the same thing. This is actually that ice field up there we were looking at. We were up here in the very slow part. That's Hubbard Glacier, the one we were just flying over. And then this is Malaspina Glacier, and we'll look at some data from that. This one flows out onto a plain and just sort of spreads out. They call it a Piedmont Glacier, and it's really interesting. And when we get to the Mars stuff, I'm going to remind you of that because it'll look pretty familiar. This is another velocity map that shows this, has scale bars, so you can actually see some of these are up to 5 meters per day in their flow, which is a lot. And in fact, some of when they're surging, like the one I showed you where it's surging, be twice that, 10 meters per day. So it's a very active area. One of the things we're doing is looking at how they're retreating and forming all these big proglacial lakes at the end, which then sort of have a runaway effect on calving and ice loss. Okay, for surface elevation, and you want to monitor that, if you monitor it repeatedly, you can get change and see how the glacier is thinning. We use typically a scanning laser altimeter from aircraft. So this is the plane we mostly use in Alaska. It's a single turbine otter, and there's a big hole at the bottom. You could actually fit through that if you wanted to, but we have a plate over the top and a laser scanner. This thing scans back and forth super fast and makes a map of the surface. And you combine that with geodetic quality GPS and attitude information from the plane, you can reconstruct the surface very accurately to about 10 centimeters precision. So then you repeat that every year, and you can actually map the change of the surface. And University of Alaska has had a program going on for over 20 years to monitor certain glaciers. Okay, my favorite technique is radar sounding, and I use that, and other people use it to get at the thickness of the ice and to map the topography underneath the glaciers. So the reason this works is radar is sensitive to the electromagnetic properties of materials, and freshwater ice, as it turns out, is basically transparent to radar waves, as long as they're long wavelength. So like police radar, weather radar, that doesn't work. It's very super short wavelength. It's high frequency. It just bounces off the surface. But if you go to meters long waves, they just kind of go right through. You do get a reflection off the surface, but then a lot of energy goes through. So this is a plane I've used a bunch in Antarctica. There's 2 antennas under the wings, and they are designed for 5-meter wavelength radar. So that's like 15 feet, kind of from here to the other end of that podium over there. So that's what a single trace might look out. You send out a pulse of energy, and usually about 1,000 to 4,000 per second, depending on the system, and you just wait and record the echoes. So it's kind of like a bat if we were flying through the room and sending out echoes and measuring the time delay and making a map. We're doing that straight down from the airplane, and instead of sound waves, it's electromagnetic waves. So you just send out a pulse and you record the power that comes back. So you have a plot of power versus time, and this is the surface echo right there, and then you get all these little echoes from within the ice, and somewhere down here is the bottom. The cool thing, though, is if you fly along in a plane, you can build up very quickly a cross-section of what's beneath you. And so this is actually an example of Antarctic ice, and this goes down about 3 kilometers. So you're seeing internal layers in the ice that are due to things like aerosols, ash, volcanic ash deposits, things like that. And people link these layers up to what they see in ice cores to get information from ice cores and then extrapolate over large areas of the ice sheet. We're not doing that in Alaska, but I had to mention it. So what about in Alaska? Well, Antarctica is easy. The ice is really, really cold, and so that helps the radar go through the ice really well. Alaska, the glaciers are much warmer, so there's a lot more water. Even if it's just little bits of water like between the ice grains, it attenuates the signal greatly. And there's all those crevasses that we saw, right? It's a mess. So you really need super long wavelengths. So we use 60 and 120 meters. The antennas are actually half that length, but we actually tow it behind the plane. So it's a little bit cumbersome, but it works. This is a little panoramic picture of us in the plane. So it's kind of like a typical day out flying. So the radar that we've built is contained in this box case that's about this big, so we can take it in and out of the plane pretty easily. That's my student, Michael Christofferson. He's looking at the laptop and untangling his headset cords, which happens a lot in the plane. But you can see the real-time data coming out in terms of the echoes. He's actually rewritten all the software for the radar and helped with some improvements and gone to the field. And he's an undergraduate at the University of Texas, but we'll be bringing him here soon. And then this is my colleague Martin Trufer unspooling some the radar antennas. We have a little video of that. So basically we just have a little drogue on the end and we feed it out the bottom of the plane. And we'll be outside. And it just spools out. It's a Kevlar rope and it's hollow inside, and so the conductor is inside and there's resistors, and so it's set up to be a good radar antenna, but it looks just like a rope, basically, a very expensive rope. Michael sometimes gets so excited about the scenery that he has to think about it really hard. He's going to kill me for putting that in there. I mentioned Malaspina Glacier. Here's a view from, I think it was Space Station or Space Shuttle. I forgot. Any idea how big that thing is? You guys, can you take a guess? There's no scale bar on there, which is terrible. Sorry. How many? 10? It's 50 kilometers across, just the white part there. So that would cover all of Tucson. And there's just a very thin spit of land out here between it and the ocean. And that thin spit of land has actually got a bunch of ice in it. And that ice is melting away, and there's trees falling in it. And so we think that this is, probably pretty unstable. And once that goes, and it's starting to go in multiple places, this whole glacier might just basically catastrophically collapse out into the ocean, and you're going to get ocean water underneath there, and you're going to form a new bay. And that could happen pretty rapidly. So we've been studying that. So here's an example of the radar data. So this is a track going from the coast up towards the mountains and then back out to the coast this way. And so you can see the surface echo from the radar moving along like that. And then the radar, the bottom is like this, and it gets a little faint, but you can track it all the way, and there's a red line that's following it. And we've measured about 800 meters of ice in that, in Malaspina. So there's some deep troughs in there. That's one of them. There's another one. So it's some of the first really good data, and we've done a big grid, and so we're mapping that out. So it works pretty well, especially in Malaspina because it's out in the open. It gets a little more challenging when you're around mountains. This is Bering Glacier, which is a really large glacier coming out of the Bagley ice field. And so going down from up top down to the bottom, you can see the bed going along like that. You see a big ridge right here, and then it goes up towards the ocean. In this one, you can't see the surface echo. We're using a different radar, but you see a better bed return. So we use the laser for the surface and then the radar for the bed. But it goes down, again, about 800 meters. We've actually gotten over 1 kilometer up here, and then up on the Bagley over about 1.6 kilometers. That's where we stay when we're doing our work. Okay, maybe not. That's a really cool old mine, though. Just a little bit about what we do. We stay in slightly better accommodations. We're actually fortunate to be able to use a lodge that's kind of remote on the Chitna River, and you just fly up this valley and over these mountains. You're up on the Bagley ice field, and then down the Bering Glacier, and you're at the coast. You can only get to this by airplane, so there's not too many people there, but there's a lot of airplanes. And when we get a day off, sometimes we hop in our planes and fly out to the coast, land on the beach, and go for hikes and look for whale bones and stuff like that. And if every once in a while I show up and my friend Chris has just caught a bunch of salmon and set up a radar lab in his garage while he's cleaning fish, which is not a bad deal. All right, so Mars, let's shift gears. Now that you're experts on airborne radar, and glaciers, we're gonna go to Mars and see what's there. Now, you guys probably all know that there's ice on Mars, no big surprise. You can see the polar caps, and people have seen those for a long, long time. And we know they're not CO2 ice because CO2 ice is so weak that it would just collapse under its own weight and spread out. And you can actually tell just from the shape of the polar caps that they have to be mostly water ice, not CO2 ice. All right, so let's start though at the North Pole. Oh, wait, forgot about this. Little Mars-Earth comparison, just to review. Mars is about half the diameter of Earth. It's about 70% the density of Earth, makes for gravity that's about a third of the Earth. The average surface temperature is around minus 65 C or minus 85 Fahrenheit, but I mean, when it's that cold, who really cares if it's Fahrenheit or Celsius? The atmosphere is less than 1% of Earth. So to give you an idea what that would be like, if you buy a lot of helium balloons and attach them to your lawn chair and you go up to 100,000 feet on Earth, that's what it would feel like on Mars. So don't do that. On Mars, the atmosphere is about 95% CO2. So for our purposes, the thing that's going to be really important for the rest of this section of the talk is that water ice is not stable at the surface below about 60 degrees latitude. And liquid water is not stable anywhere. So for you chemistry enthusiasts, here's the phase diagram of water, solid and vapor, and this is supposed to say liquid up there. Earth sits up here. If you move up or down in temperature, you can get into the solid, liquid, or gaseous phase very easily. Mars, you're down here in terms of pressure, down here in terms of temperature. Mostly solid. You can get into vapor. You can kind of maybe get into liquid temporarily every once in a while, here and there. That's under a lot of debate right now. So the important thing is that it's hard to have water ice at the surface outside the polar regions because it'll just sublimate away. If it snows, it just goes away instantly. So the North Polar Cap of Mars, just a quick overview of the ice that we know about or have known about, different types of ice. It's about the size of Texas. And I had to put this in. I mean, this was in my talks previously, so it's still in there. I don't have one for Arizona yet, sorry. But it just happens that the area is really close to the area of Texas. And when you're in Texas, you got to relate everything to the size of Texas, you know. That's all that matters. Of course, when you're in Alaska and you're doing field work and people find out you're from Texas, they love it because then they get to tell their favorite joke of all time. They're like, oh, do you know what would happen if we divided Alaska in half and had 2 states? And you have to say, no, what? And they say, well, Texas would be the 3rd largest state. They just start laughing. I love it. But it's true. Alaska is really huge. And some people think Texas would be better off if it was covered with 2 kilometers of ice. But we'll go there. If you melted all that ice, it would cover the planet in about 9 meters of water, which is a lot, right? That's a lot of water. And the South Pole was a little bigger. It's about 11 meters of water. So overall, if you melted them both, somehow, you could have a lot of water. We know there's high latitude ground ice. So the Phoenix lander, which was a U of A led mission, was at 67 north. It excavated down to some white stuff that sublimated away, and they were convinced it's ice. The thrusters appeared to have actually blown away some surface debris to get down to the ice. That was really, really cool. And then Shane Byrne here at LPL has led an ongoing study looking at fresh impact craters that expose water ice right below the surface down to lower latitude, like 45 or so latitude, which is really cool. I mean, we don't know how deep it is or anything, but there's ice there. So what about these things? Back in, so the Viking missions were in the 70s, returned a lot of the first comprehensive global imagery of the planet, and then people noticed all these sort of pancake-like smooth things surrounding mountains, abutting ridges and things like that, and were very curious about them and started studying them. So one of the interpretations that was put out there was that these things are basically debris flows, or basically the mountains are falling apart and shedding material, and that maybe there's a little bit of ice in there somehow, or there was, that helped it flow out, and that ice is probably not there anymore, because nobody back then could really imagine that you could have any ice at these latitudes. It just didn't make any sense, so nobody even thought that it was possible, or not much ice anyway. It wouldn't stick around. So there's a couple of examples of these weird things filling in valleys and everywhere. Whoops, that was not the button I wanted. Didn't even realize that was an option. We could quit. You want to quit? Okay. So a couple of people, including Barbara Lukita at USGS, compared some of the larger features that filled in valleys to big glaciers on Earth, like Berg Glacier in Antarctica. Now keep in mind, there's no ice exposed anywhere. It's all rock and dust. It just looks the same as everything else. It's just shaped differently. But this went on for a long time. Basically, nobody knew what the answer was, what this stuff was. But there were also other interesting Viking era discoveries, such as the face on Mars, which I'm sure you've heard of, but you may not have known that NASA had a big cover-up of a whole city that was near the face, and you can read all about it on dudeman.net. But it's an example. The reason I brought it up is that better data actually helps. So we went to much higher resolution data. This is high-rise on Mars Reconnaissance Orbiter. It's another U of A led. It's a U of A led instrument. Alfred McEwen here's the PI. And then this is a perspective view from HRSC on Mars Express, a European mission. And you can see, yeah, it's a pretty cool hill. And but it just happened to look like a face. It really did, which is kind of cool. All right, so this is a HRSC perspective view of some Mars Express of a low-bait debris apron. So this is a nice one because it pretty much surrounds this massif, scale bar this time. And this is what they were calling low-bait debris aprons. And so we call these LDAs for short. Just, we can't help it. We still call them that. So you can see these kind of lines and things like that might be indicative of flow. We'll zoom in some more. First off, sorry, more Texas stuff. City of Austin for scale next to one of these things. These things are huge. I mean, if there's ice in them, that's a lot of ice. And you could, park a giant colony next to one of these things. So I don't know how Austin compares to Tucson, but it's pretty similar in size. I think you can kind of get the idea. More people in Austin, though. That's the problem. Okay. So we're going to zoom in on that same thing right there. There's a swath kind of going across here using CTX imagery. We're going to keep zooming in. You can see all these features that really just looks like somebody poured molasses, a giant vat of molasses, and it flowed on the surface, and then it froze. And you can see all these things we call compressional ridges and flow lineations. You also see impact craters, and they're not deformed. And that shows you right there that these things are not flowing very fast, or if at all, and you don't really expect them to flow in the temperatures we have right there. But the craters are useful in determining the age of these things. Another little perspective view. This is sort of cobbled together. Sorry for the poor quality, but it gives you an idea of what it would be like sort of flying by one of these things and looking down. Here's their distribution on Mars. This is a map made by Joe Levy, and he's broken them down into the LDAs, which we were just talking about in green, and then these other features, lineated valley fill and concentric crater fill, which basically look like the same stuff, but they fill valleys or they fill craters. There's a lot of them. And the age based on those craters is hundreds of millions of years. So that's pretty old. It's way older than any ice on Earth. But it's also fairly recent. So in geologic terms on Mars, it's part of the same recent geologic era, excuse me, that has been going on for the last few billion years, which is basically a very cold, dry desert. So conditions have not really changed at all, that we know of during that time. So it's still kind of weird. So the debate went on for a long time whether they're debris flows, which is just a little bit of ice, interfilling the spaces between the rocks and enabling flow. And they could explain that away with slow diffusion of water from the ground maybe, or through frost from the atmosphere getting in there, and the water ice could be long gone. The other hypothesis is that they're debris-covered glaciers, which would require a lot of atmospheric deposition, basically snow. So it has to snow at those mid-latitudes on Mars and then stay there and accumulate and build glaciers. And you'd still have to have that ice there to maintain their shape. So since that didn't make any sense with the current climate, nobody bought into this. So, but years passed and people started thinking, well, okay, sorry, this is the same thing. Basically, water ice, why not glaciers? Why did people not consider this very likely? It's because of the stability issue and the temperatures. Like you can't, if you could even get it there, how is it going to flow? Have to be a lot warmer, most likely. So this idea came along, is that basically the orbital parameters of Mars are pretty different than Earth. And the spin axis tilt, so the amount of tilt relative to the ecliptic plane is the obliquity. And that value for Earth is this little wiggly line right here in the middle. It only varies by a couple of degrees. And those little wiggles cause ice ages on Earth. But Mars, so Earth has a big moon, which helps stabilize its orbit It's not as sensitive to the resonant. It's not resonant with other planets so much. But Mars is obliquity. If you go back in time, so left is now. It's currently very close to Earth's, coincidentally. But if you go back in time, it gets these big wiggles, and it was much higher. So the idea is that at low obliquity, like now, the water ice is mostly stable at the poles where it's colder and there's not a lot of incident sunlight. But at higher obliquities, such as these, the water might move from the poles through the atmosphere and redeposit at lower latitudes. So you basically just move water around. A little different than on Earth, because Earth has oceans, and the ocean can put all this, water in the form of ice on lands and grow these giant ice sheets. But same basic idea. So this started getting some traction. People started looking at layered deposits and thinking, well, that's driven by these orbital signals, and maybe that's a real thing. But so how can we answer this for these features? Like, what are they? Well, what do you think? SHARAD, radar. So Mars Reconnaissance Orbiter came along, and this is a great NASA mission. SHARAD stands as an acronym for shallow radar. It has a 15-meter wavelength. So if you remember, that's longer than the Antarctic radar. It's a lot shorter than the Alaskan radar, and it's from orbit. So you're 300 kilometers up. It's still going. The mission's still going. 12 years later, which is fantastic. And a cool thing about this is it was contributed by the Italian Space Agency. This is a NASA mission. All the other instruments are U.S. And this has been an interesting experience. They're great to work with. They build great radars, but there's been some cultural, some learning going on there. When we they spent years just planning this mission, designing the radar, everything, putting it all together, integration testing, launched it, got to Mars, aerobrake, got into orbit, started taking data, everything works. And then a few months later, we're in a telecon, and the Italian side, the leader on that side says, well, we're going on vacation for all of August, so we're just going to turn off the radar. See you in September. And there was just silence on the telecon, and the lead on the U.S. side is like, excuse me? Could you repeat that? And then we were all just like, what are you talking about? You can't turn it off? Well, they did, but we talked them into just doing 2 weeks instead of 4, and it came back on. Everything was fine. We were just petrified it wasn't going to come on. But they've been fantastic to work with, and they built a fantastic radar. It collects beautiful data. And I know you're thinking that this is fake news, but this is all true. Except I'm pretty sure it's not as more important than the toaster waffle, because I don't think my son would be alive if there weren't toaster waffles. All right, back to the North Polar Cap of Mars. Got a little video made by NASA showing exactly how SHARAD works. Oh, sorry. So that's the spacecraft. This is the radar antenna. It's 15 meters long, just like the wavelength. So it goes along, zaps the surface, going across the North Polar Cap. Now it's going to, this is a little liberty taken here by the artist. That doesn't really happen. It doesn't glow. But there are layers inside, and there's the bottom, and we map all that, and it's pretty cool. So now it's going to rotate around and show you what the actual data look like. But it's a fantastic data set, and we now have thousands of orbits crossing the polar caps of Mars and can build up a 3D volume of the data, and so which is actually way better than anything we have on Earth for Antarctica or Greenland. And that's about 2 kilometers of ice right there. So it's not too different than Greenland or Antarctica, really, in that sense. Okay, now for the kicker. This is SHARAD data over one of these LDAs. Where the spacecraft's going along this way, hit the cliff. Well, it didn't hit the cliff, it flies over the cliff. This is the plane right here, so this is the surface echo, and then you hit the edge of this and it splits into a surface and a bed. And well, we've determined that it's the bed through lots of verification, which I won't go into. But it looks really similar to the Alaskan Glacier I showed you, right? There's a sharp surface echo, there's a sharp basal echo, and there's nothing in between. This is kind of surface scattering off these things. But basically, it's entirely consistent with pure ice. And we were kind of amazed that this worked from orbit. But the ice is super cold. That helps a lot. And it's pretty pure. So this is a little bit of math here. We use the time delay of the radar from the surface to the bed. And then we assume that the bottom here, the plane continues underneath, basically flat. And we back out what the velocity of the radar wave has to be to make that work. And it pretty much has to be pure water ice. You can't use CO2 ice. You can't use rock. You can't use a 50-50 mixture of rock and ice. It has to be like 90% ice, water ice. And it works everywhere we do it. So we now know that these radar properties are consistent with the debris-covered glacier hypothesis. That's just one example, but it works everywhere we do it. The debris layer on top we think is less than 10 meters thick because that's the resolution of the radar, and we only see the top. We don't see a bottom echo from the bottom of the debris. So there must have been a climate that was favorable to glaciation in the past, like an ice age. And we've learned that a pretty thin protective layer can protect shallow ice at the mid-latitudes for many, many millions of years, which is pretty cool. That means there's probably a lot more ice than we even know about on Mars, and we're finding it all the time just under the surface. Another reason, another cool thing is that people are talking a lot about sending humans to Mars, and humans need water, and rockets need fuel, and you can make rocket fuel from water. So we're working on trying to evaluate how deep this ice is from the surface, how much there is. This is a study by my work of Eric Peterson, who just got his PhD and came here as a postdoc. He focused in on this area right up here. So I'll just show you a little results of this survey and just see how much water ice there is. This is a big area, so like the size of Texas. And this is all the blue stuff looks like it should be glaciers or, containing ice. And then Eric checked the data in all these Sherrod tracks, and it worked in all these yellow ones. It didn't in the red ones, but he later determined in a separate study that that's due to surface roughness scattering the radar. They look the same, and so they should be the same, but we can't totally confirm it with the radar. But just looking at the volume of ice in all of these, it's about 100,000 cubic kilometers. That's about 4 times all the Great Lakes combined, just in that one area. And that's only about 40% of all the LDA, which is only one fraction of all those things that have been mapped. So a lot of water. Okay, so we've got answers, but new questions. How does the protective surface layer form in the first place? How thick is it really? Is it like 1 or 2 meters? Who knows? If it's 10, that's a bigger engineering challenge, a lot different engineering challenge for people to get to than 1 or 2 or 3. How did they flow? Was it just very incredibly slow over 100 million years? Or has it been episodic and somehow has been warmer and we don't realize it? So this won't be long. Just want to take us back to Earth and say, okay, now that we've seen all this stuff on Mars, let's go back to Earth. What can we find that will help us understand what's going on Mars? So turns out rock glaciers are these features that have largely been ignored by the community and just not really, people don't know much about them. So there's actually a lot of recent attention given to rock glaciers. Basically, this is not a rock glacier, by the way. This is a glacier with a bunch of debris coming out onto the surface, which may be one way you create a debris-covered glacier. But there's a lot of things around that look like glaciers, but they're covered with rock, or they are a bunch of rock, and we just don't know. It's the same thing as on Mars. But we can get to them, we can study them, we can study their motion. It's a lot easier to work on the ones here on Earth. So back to some of these big glaciers in Alaska, one way you get debris on top is these moraines. And every time a glacier merges, you get another moraine. and then eventually it just covers pretty much the entire glacier. You get little slivers of ice sticking out, and then sometimes it's just like you can't even see the ice. This is the end of a big glacier here, and this is the plain. This is not glacier. You can hardly tell the difference. And there's another view of one, and look at this little weird thing down there. We're pretty sure this is an alien landing site, and that we just don't ever catch when the rocket comes out or something. So I'm really not helping conspiracy theory stuff, am I? So another way is just debris flows or avalanches off the sides, and these are just happening all the time here in Alaska. So this goes out, and then it starts moving down the glacier. You get enough of these, and it covers it up. And sometimes you can't even see any ice except unless there's like a melt pond or something like that. So this is one that we decided to start looking at in detail because it was close to where we based our other work, and it's really cool, and it looks a lot like the Mars glaciers. Instead of being confined to a valley, it comes out and spills out. The trees are a little different, but we can ignore that. So anyway, it's really cool. It's pretty small. It's just like a kilometer or so across. So it's really too small to do airborne radar over, but you can access it. Here's some more pictures taken from the plane. Got similar lobate front. It's actually pushing down trees along the edge. It's advancing. Sorry, I'm getting in your way here. You've got compressional ridges like on Mars. You do have little pockets of trees moving along, which is different, but anyway, it's really cool. Very, very interesting thing. So going into this work, we were wondering, is it really a rock glacier? That's what they've called it, and everybody thinks it's mostly rock. Or is it really a debris-covered glacier? If so, can we map the debris and ice thickness? How fast is it moving? And is it a good analog for debris-covered glaciers on Mars? Because if it is, then we can do a lot of cool stuff. So our methods, surface geophysics, just get out there and do stuff right on the surface, and then airborne scanning LiDAR, or the scanning laser, and photogrammetry. So I'm going to run you through a little bit of that. So these things look, smooth in imagery or from the air, but then you get down on the surface, and it's actually it's a lot of work to hike around on these things, especially if you're carrying a pack full of batteries like these guys are. I should have included Stefano's plot of how many times he fell carrying batteries versus how many times he didn't, and his argument for getting newer, lighter batteries. It's a pretty good one. And you got to be careful. Things are super loose, and you could end up like this former grad student here. I mean, Moose. This is but doing GPR or radar on the surface is a little challenging. This is, it's easy in the plane in a lot of ways because you just fly over it. When you're doing it on the ground, you've got these like a transmitter antenna and a receiver, and you have to move along like every 10 to 20 centimeters. It takes forever. And also it's a rough surface, so you actually don't get really good coupling. So this was actually in Utah, up in the Uintas, where we tried this the first time, and we learned a lot about how not to do it. But we did some at Sourdough, and it worked, but not too well. So we thought, how about skiing it? So Eric and Tyler went up this last March and built a radar sled and rigged it up so they could ski along and actually take data. So it's a snow cover on the debris well, you'll see what it is. It was still not easy. Those guys, I think it was a lot of work. It was cold. They worked really hard and they got some good data. It was a great learning experience. So here's a few results. This is a little profile right up here from A to A prime. And the cool thing about this is you can really see the bottom of that debris layer. It just kind of comes in really strong. And it kind of varies between 3 and 5 meters, which is about right. I mean, about what we would expect. And then, well, at least that looks like a debris layer, right? We don't know yet what this thing really is. But then down towards the base, so this is a little transect down towards the toe of the glacier. They could see there's this going up the surface. This one's corrected for topography, so you actually see the slope. and then a nice booming bed return down here about 30 meters down, which is exactly about where you would expect the bed. And then you do have some stuff in the middle, but it's pretty clean overall. There's no, if it was all rock, you would not see the bottom. Here's a big profile across the toe down here, 8A prime. This is a big one, and it's beautiful. You get the bottom of the debris layer all the way across, and then a nice bed return going down about 40, 50 meters in places. So far, based on this alone, we think, yeah, it looks like it's ice and not so much rock. We've also done some airborne work. This is my friend Chris's plane, and he's got it outfitted with he can put his scanning laser in there and do the photogrammetry. So basically a nice camera pointing straight down. So this is a laser-derived map of the surface. That was the first thing he did that sort of started off this project. But we also get, when we do this, an orthophoto mosaic. So this is about 500 photographs stitched together seamlessly. And it has 25 centimeter sort of pixels, pretty much like high-rise on MRO. And notice how it looks. It looks like, oh yeah, I could walk on that, no problem. So that's the problem we have for Mars, is until we have better, even higher resolution imagery and morphology of the surface, it's hard to plan like landing on something like this and actually being mobile. Then it gets cool when we do repeats, because then we can actually get surface change, and we can both map the surface topography change, but also the velocity change. Dang it, that button is way too easy to hit. But I'm getting more exercise, so that's good. All right, I'll try to get through this quick. There's a change detection map of the surface where you can see actually basically the ridges have moved forward, and that gives you a change in surface topography. And then, sorry for the resolution on this, couldn't find the original. But we get a surface velocity map, and this is a first cut, and we're seeing up to 2 meters per year. So compared to 5 meters per day, this thing is really slow, but it's moving enough that we can detect it, and we can map the change and map the velocity and then relate that to everything we see inside. So our first answers, it looks like a debris-covered glacier. Like on Mars, the debris is a few meters thick. We can image through to the base with GPR, which is great. We can quantify change and contain a velocity field. So we can say it's actually a glacier. He's going to kill me for putting that in there. But mainly, it's a great laboratory to help understand Mars. So we actually just heard we got funded by NASA to go back and do a bunch more field work there at a similar site in the Rockies in Wyoming, where there's a nice there's a bunch of them there as well. They're actually harder to work in because they're at higher elevation and they're harder to get to. But we also learned that you got to look out for some wildlife, be prepared for moose and bear, all that sort of thing in Alaska. Those things are huge too. It's ridiculous. So we have a lot to learn about debris-covered glaciers, both planets. I feel like there's still a lot to learn about Mars from those data sets, but we're still getting new data, and we're thinking that we can steer future mission directions. And then we think that the Earth examples are really great opportunities to learn about active processes, linking them to the composition, structure, and then we can hopefully turn that back around and then apply that to what we see on Mars and learn about the flow history, internal structure, climate history on Mars from looking at these things. So I want to thank all these organizations, people that have contributed to all this work. And then I've got this one little cool thing, which if it works, it looks like it's not working, but it usually works. It worked. This guy put this together from high-rise imagery and topography, and it's just like a little video as if you were flying over one of these things on Mars. And the details is just astounding, and you can see all these like shear margin crevasses along the side, little ripples on the surface, everything you would normally see on an Earth glacier. It's covered with dust and rock, but it's just amazing. It looks just like you could get this somewhere in Alaska or Patagonia or Himalayas. Almost done. Best part's to come, though. There's a little impact crater.
How much distance is this cover?
I don't know offhand, but I'd say it's about 5 kilometers from the top to the bottom, max. All right, so that's a similar, very similar one. It's about the same region. So that's all I have. Thank you very much for coming. Happy to answer questions.
Thank you for that talk, and we have time for a few questions.
Is the high-rise imagery, is there enough repetition and resolution that you can detect any motion of these things?
Not so far. And based on just the temperatures, and if we, say it's 100% ice, get the topography, the expected motion would be on the order of like a micron per year. So, yeah. I mean, it's still worth looking, I think, just in case we're wrong, but we'd have to be imaging for a very long time. Bert, you got somebody over here. There.
One of the future Mars rovers is supposed to be able to drill down below the surface. Do you know if there's any plans to go to one of these low-bait areas?
They are not going to go to one of these areas. Yeah, they're going to lower latitudes where they don't expect ice in the near subsurface. In fact, it's a bit of a catch-22. NASA, once you know there's ice there, they call it a protected area. And because they don't want to contaminate it, they want to make sure that if you did go there, you'd have to have a completely sterilized spacecraft, everything about it, so you wouldn't potentially contaminate it. Yes?
I'm not afraid of contaminating Mars personally, but some of the slides seem to indicate a high purity of water on the Martian glaciers.
Yes.
Do you think that could be partly due to the low gravity not grinding as much rock up and the moraines being a little bit less?
Well, that's a good question. They've clearly had a lot of rock fall on top of them that's been carried along and moved along. But I suppose you could, I'd have to think about whether that could be a factor when the glaciers are forming themselves. Like if they form fairly rapidly and you're not able to entrain as much rock because it's not coming off, because the rock strength is going to be the same as Earth, but the gravity is less. So, yeah, maybe.
Can you use the craters on these stuff to constrain the thickness, at least for a lower limit?
There's actually a paper just out in Icarus about that. Dave Baker and Lynn Carter, who's here, and they've attempted to do that. The conclusion is that it's probably fairly thick, but on the other hand, you don't see like tens of meters perhaps. But you don't see the expected radar return at the bottom of that layer, so you have to explain that, which is a little hard. I'm waiting on the next generation radar, which will be higher resolution. It may not probe as deeply, but it should map the debris layer pretty well.
So Mars loses a lot of, or it was theorized it lost a lot of water to space.
In a long time ago, perhaps, yeah.
When the obliquity of Mars changes, you said the water gets repositioned. How does it get repositioned as opposed to being lost to space?
Well, that's a really good question. So it gets repositioned by sublimation into the atmosphere, carried to somewhere else, and then snowfall. I would think that if you're doing a lot of that, you're going to lose more to space each time, but it's probably not a huge amount. Because according to the models, it actually happens fairly rapidly. So maybe a few thousand years or 10,000 years max, which is pretty short, pretty quick. So it's probably not resident in the atmosphere all that long.
Do you see lateral moraines on Mars?
So that's a good question. There are places, this slide isn't too bad. You can sort of see in this imagery some lineations this way, and it's hard to tell what they are, but if you look in thermal imagery, where are you? I lost you, sorry. If you look in thermal imagery, you can see evidence for striations that tend to come out from these like ridges, and
In that direction of flow, though, right?
in the, yeah, so that would be a lateral moraine on the sides.
Right. Or a medial, right? 'Cause it's,
Well, see, these are kind of weird because they all connect together in these situations. It's almost like a bajada, alluvial fans that all join together and make this one giant apron. So there's not really an edge, but that's the closest thing we see to moraines, except like in that, let me see, like that is a pretty good, looks like a terminal moraine. They're very uncommon though, and that's been a big question because, out of the thousands of these things, you only see a few. And it seems to be like this is lineated valley fill out here. This is probably several hundred meters of ice in this valley, overlain with rock and dust. And then this is a little glacier coming out on top that's probably much younger. And those moraines tend to show up more in the most recent, youngest ones. Nobody really knows why. Microphone coming at you, Sarah.
On the Sourdough Glacier, the
Yes.
the debris-covered glacier, if it's not accumulating snow every year like a regular glacier, what is driving the motion?
That's a great question. What we think is it was accumulating mostly probably during the Little Ice Age, several hundred years ago, and became covered with debris, and basically the ice is just kind of like a big slug of ice moving down the hill now. And you see a lot of this. You still could accumulate a little bit up here each year and kind of entrain it in the rocks. It's probably getting rockier and higher rock content. That's actually part of a whole nother part of Eric's thesis, looking at the one in Wyoming, looking at sort of episodic accumulation and then rockfall. But if you look in the Sierra Nevada and the Rockies, you see a lot of these things where you've got basically a slug of ice covered with rocks or a rock ice mixture, we don't really know, that's moving down the valley, and there's a big kind of concave, like an empty area up top where it used to accumulate, and it's just gravitationally oozing down. At least that's what it looks like. We don't have any good measurements on those yet.
Have you done any modeling to consider the gravitational differences on Mars and Earth, and also the probable lack of air bubbles in the Martian glaciers to see how the dynamics of the ice would be different?
Yes, there's a few people who are working a lot on modeling these things, and they definitely take into account the gravity. The structure of the ice in terms of ice grain size is a really big factor and can change the results a lot. And so actually the Sherrod results, which constrain the dust content or the internal like dust lithic content to less than about 20%, helped those models a lot. But they don't assume there's any air bubbles in there because it should be compacted enough that it's just solid ice at that point. But yeah, that's an ongoing problem. A few people are working on that, and one of the things that's needed for that is more lab experiments of rock ice, dust ice mixtures at those temperatures.
All right, cool. Let's thank Jack again.
Thank you.